And the last lesson in the chapter, 10.9, Inductance. Induction is the process where EMF or voltage is induced by changing magnetic flux. Mutual inductance is inductance of one device to another, like a transformer. Change in flux is usually done by changing the current, since they are solid pieces. Otherwise, we can change the magnetic field or change the area or the angle. Well, changing the area and the angle is pretty hard if they're solid pieces. So we'll change the magnetic field, and the magnetic field is based on the current of the first coil. We can reduce inductance by counterwinding coils. If you have to have a coil, you wind half of it one way and then the other half the opposite way, and the magnetic fields then would cancel out. So the EMF produced by inductance is negative M, change in current over change in time. M is the inductance of the coil. M is the mutual inductance. Its unit is the Henry. I is the current. T is the time. And of course, EMF is the induced EMF, or volts. Self-inductance is a changing current in a coil causes a changing magnetic field in the middle of that coil. Well, the changing magnetic field in the middle of the coil causes some induced EMF in the same coil. This resists a change in the current in the device. So you have this current going, making this magnetic field. The magnetic field, as it changes, induces a current and an EMF in that same coil. And by Lenz's law, it's going to be resisting the change. So that means the current is going to try to stay constant. So we can use these inductors to try to keep the current constant. So it's the EMF is negative L, which is our inductance, change in current over change in time. So L is the self-inductance in henries, and I was current, T is time. All right, so if we use Faraday's law, negative N equals change in flux over change in time equals our EMF, and that also equals our self-inductance, we can take that and we can solve it for L. The time should cancel out, so L equals N, the number of loops, change in flux over your change in current. For a solenoid, remember that's that really long tube. It's caused by wrapping wire like around a long tube. The self-inductance is that, where mu0 is the 4 pi times 10 to the negative 7. N is the number of loops, A is your area of the loop, and L is the length of the solenoid, the little l. Inductance, mu0, N's number of loops, A is cross-sectional area, little l is the length of the solenoid. So let's say we have a current through a little inductor and it's switched off in that amount of time. What EMF is induced to oppose this? Well, our EMF is negative L. This is a self-inductance because it's only one device. Negative L, change in current over change in time. Well, the L, they told us, was 7.5 millihenries. Milli is times 10 to the negative 3. Our current, well, change in is our final minus our initial. So our final current is being turned off. So our final current is 0, and our initial current is the 4 amps. And our time is right there. That's the amount of time it takes for our current to be turned off. So our EMF produced is 3.6 volts. We can also store energy in an inductor. I'm not going to drive it for you, but the energy in an inductor is 1/2 the inductance times the current squared, where E is energy, L is inductance, and I is current. That's all I have for you today. Have a good day.